Okay, if y'all would go ahead and do the seating chart right now. And don't forget that if you are on Zoom, your name needs to go down here. So if you're on Zoom, you put it at the bottom. If you are in class, put it where you're sitting. A few minutes, I think. 2 minutes. Please make sure that once you leave the spreadsheet that your name's there. So go back and double check, make sure it's there. So make sure you have your best friend. You're gonna need your best friend. Because remember, we're starting iClicker again today. So make sure you have your best friend. All right, so happy Tuesday. What do you get when you cross a snowman and a vampire? Frostbite. But it was cute. Okay, I have to tell you about yesterday's because I really enjoyed yesterday's. I'm not sure why, but I did. All ready? What do you call a man lying at your door? You call him Matt. You call him Matt, like a Matt, but this person's name. It's funny. I liked it. Okay. So, few things we got to talk about. Let's see. In case we don't finish chapter 3 today, in case we have to go into chapter 3 on Thursday just a little bit, it's kind of looking like we will. I moved chapter 3 homework to be due on Friday instead of tomorrow. So just in case, regardless of what happens, I moved it to Friday. And I've moved it on the calendar. I moved it on the Pearson website. I think there might be one place in Moodle that I forgot to move it, but I'll go double check. There's so many places. All right. Oh, and the other thing I wanted to show y'all. So I know that this chapter is really, really dense, especially for those people who haven't had chemistry or haven't had chemistry in a long time. So if you scroll down, we did unit 1. If you go to unit 2 and you open the chapter 3 material, it looks just like every other chapter. I can do this, where it's got your lecture slides, it's got your in-class problems, and it's got all the videos. But if you go all the way to the bottom, a couple of people were asking for extra videos on whatever it was. It's a bunch of different topics. So what I did was I organized some extra videos that focus on one particular thing, and I put them here. So I thought that might be useful for y'all. So you can see it's separated by sections within chapter 3. Okay, so they're not required at all. But if I make them available to one person, I like to make them available to everyone. Okay, so if you need them, they're there. Okay, and you'll see I changed on the calendar, chapter 3 homework being due on Friday. Okay, and you're doing your seating chart. All right, so ready for some iClicker? Okay, here we go. I'm gonna do a poll. Okay, here we go. So remember, you get a minute and then we'll switch up and we'll give y'all a minute to talk together. So right now you're quiet. You're not sharing with others. Okay, here we go. How many valence electrons? Whoa. How many valence electrons are in an atom of magnesium? You shouldn't have to purchase it if you did the book bundle. How many people, raise your hand if you're having a problem because of the book bundle? Oh my gosh. Okay. Okay. No. If you, here's the deal. If you purchased it through the book bundle, it is a sin for y'all to have to pay for it again because you paid for it with the book bundle. That was the point of the book bundle. So I don't want you, right now, do not put in your credit card. Do not buy it right now. I'm going to pause iClicker questions until Thursday to give y'all a chance to call the bookstore because the book bundle was through the bookstore. It's nothing that I can do. Like I can't fix this for you. It's either the bookstore or the iClicker website. So if you go to iClicker, like Google iClicker student support, and it'll come up with it. Question. So go to the bookstore and tell the bookstore, like this was the problem. And so I bought it and see if they will somehow talk to iClicker and iClicker can refund you because you paid for it. That was the point of the book bundle. You guys are not supposed to have to pay for things twice. I am super unhappy about that. I will call the bookstore as well. I might not be able to call them today, but if I can't call them today, I will call them first thing in the morning tomorrow and let them know that it's happening to a lot of people, but it has to come from you. You guys have to go and say, I bought the book bundle, you know, it gave me the temporary subscription, but now I can't get in. Okay. So I can't do it for you. So you have to do it. Okay. But don't pay for it twice. Please don't pay for it twice. Okay. All right. So I'm going to not grade. I'm not going to grade this, but we're going to do it because I think it's really helpful for y'all. All right. So how many valence electrons are in an atom of magnesium? Call it out. 2. How'd you know that? Because it is in group 2. So it has 2 valence electrons. Okay. All right. So, all right. Elements in group 8A or 18 are called noble gases because they have blank valence electrons, except, remember for our exception, helium, which has 2. So how many? 8. It has 8. Okay. All right. Let's see. Okay, how many protons and how many electrons are present in the sulfide ion S2-? So first, let's look at protons. Look at S. On the periodic table, it's in column 16. How many protons? We have 16 protons. And how many electrons? Now be careful with this. It has a charge, an overall charge of +2. So if we have 16 positive, not 6, 16 positive, how many negatives do we need to get to +2? We need 14. We need 14. Right? Because we want an overall charge of +2. Make sense? Yes? No? 16 minus 14 is 2. Okay. All right. So 16, what do we say? 16 and 14 right there. Okay. So what ions are formed when magnesium transfers electrons to chlorine? What are we going to do? Mg and Cl, right? Tell me about magnesium. Go to where? Periodic table, your best friend. What column? Column or group 2. So what's the charge going to be on magnesium? +2. How about chlorine? What group is chlorine in? 17. And we know 17 has 7 valence electrons. So they just want to gain 1. So that would have a charge of -1, or you just put the negative, right? So that would be C. Okay, you want to do one more? This is so not the same. I'll give y'all a few minutes on this one. I want you to really look at this one. Select the correct match between name and formula unit. Try it right now. I'll give you 2 minutes or so just to kind of think about it. I'll come up with an answer. You need more time. Raise your hand if you need more time. You? Okay, I'll say 3, 2, 1, and then tell me your answer. Ready? 3, 2, 1. B. B is correct. Okay, so let's look at each one real quick, right? If we're doing potassium chloride, K, right, is a charge of, first column, +1, Cl, halogen, group 17, so -1. So what would your formula be? Simply KCl, right? One of each. So does that match? No, so it can't be 1. So y'all said magnesium sulfide, and that's how you know it's not a polyatomic ion, it's an anion, right? It's not sulfate or sulfite. So the magnesium is in group 2, so it has a charge of +2. Sulfur, group 16, charge of -2. You crisscross them and you get Mg2S2. Can you leave it like that? No, you must reduce, okay? How about aluminum fluoride? Aluminum we know is always a charge of +3. Fluoride, -1, it's a halogen. So we get AlF3. That does not match what was given. All right, 10,4 oxide. 10 is SN. It's a transition metal. So why did I put a +4 there? Because of my Roman numerals, So I put the 4 there. Now oxygen, I know that oxygen is always going to be what? -2 because it's in group 16. So then I crisscross and I get SN2O4. Do I leave it like this? Why not? Because you can reduce it. So how does this reduce? It should be SNO2. SNO2. So this one is not right. right? These weren't right. This wasn't right. Last one, copper 1 bromide, same thing. The 1 tells me it's a charge of +1. Bromine always carries a charge of -1. So crisscross, you get CuBr. So that's not right. You'll likely see something like that on an exam. Can you do that? Okay. All right. Okay. So let's go back to our ICP. All right. So before we go into section 4, there's one thing I want to touch on real quick. Is that I want to talk about what if you're given a formula or given a name and you need to say what the ion is, right? You remember in the past when we said, okay, what's the formula, right? But what if you're given the formula and you need to find the charge of everything? What do? So I'll give you an example. What about FeO? How do I know the charge on each of these atoms, each of these ions in this ionic compound? What do? I have to think about what the charges could be, right? What is Fe? It's iron, but it's where is it on the periodic table? It's a transition metal, so I don't know what the charge is. So I'm gonna have to figure it out somehow. What about oxygen? Do I know oxygen? Absolutely, I know oxygen. What's oxygen's charge? -2, right? And then I'm going to have Fe, and I don't know what this is. So how do I figure out the charge on iron? What do? So I typically do what's called the reverse crossover, right? If I had NaCl, I would say Na. In order to get my charge on Na, I take however many chlorines and I go the opposite way. So this would be Na and it'd be a +1 because the first element is the cation, the second element is the anion. And then I take the 1 from down here and I bring it up here and that gives that a -1. So that would be Na +1, Cl -1. But I can't really do that with iron, right? So what do? I have to know that I'm getting 1 atom of oxygen, right? And that 1 atom of oxygen has a charge of -2. So then what must my charge be on the iron? It must be the opposite, +2, because all of this together must equal to what? The definition of an ionic compound, 0. The charge, come on, Pin. The charge on any ionic compound must be 0, always. Always, always, always. So you can think about doing the reverse crossover, sure, but you have to remember that there are some elements that are always going to have a particular charge. So if I said this was 1 and this was 1, and I reversed them, right, and got a +1 and a -1, well, oxygen's not -1. So what do I have to do to get to the correct charge? I just multiply by 2. So I get Fe 2 plus O 2 minus, and that's correct. So you could think about it either way. Make sense? You want to try one more? Okay, so let me erase this. We're going to do another one. I don't have a whole lot of room. Okay, but it's the same thing that we were doing in class. Okay, how about Fe CO3 2. Now what do you have to do? Is iron a +2 here? How do you know that? Where am I going to go? CO3, what is CO3? It's a polyatomic ion. So go to your polyatomic ion table, and where do you find CO3? The first one with carbon in it, it is carbonate. So it is CO3. This cannot change. CO3, 2 minus. Okay, now what? This is what I like to do. I'll show you what I like to do. I like to still do that reverse crossover. And I would get a +2 here. And really there's a 1 here. So I would get a -1. But I know, I looked in my chart and I said, okay, CO3 can't be a -1. It's actually a -2. So what do I have to do to both of these in order to get the right answer? Multiply by 2. So my iron becomes what? 4 plus, then my CO3 becomes 2 minus, and now I'm good. That's what I like to do. I like to do that reverse crossover. You just have to remember it's like the opposite of reducing. Right? Because if I did this as the crossover, if I did Fe 4 plus and CO3 2 minus, what would I do? I'd cross, right? And I get a 2 and I get a 4, but I can't leave it like that. How do I have to write it? I have to reduce that. 2 divided by 2 is 1. 4 divided by 2 is 2. So I get FeCO3 2. So we just proved that it works. Yeah. Okay. I like that head nodding. I appreciate that head nodding. You can also do the head shaking. It's cool. I just like to get that feedback. Okay. So now we can move on. So the next thing that we have to think about are not ionic compounds, right? We said that's one way that you can get to your complete octet. What's the other way that you can get to your complete octet? You can be so nice and you can share, right? So what do we call compounds that share electrons? Covalent. So it's important to remember those valence electrons in covalent compounds as well, right? They're super important. So if I'm talking about, let's do this with the first one that we have to do, with water, H2O. Gotta love water, right? H2O. If I want to know what a covalent compound looks like, I have to understand the valence electrons that are in each of the atoms that make up the covalent compound. So what are my atoms? I have hydrogen atoms. So how many valence electrons does a hydrogen atom have? Has 1 valence electron. So you can draw that in what's called a Lewis dot diagram, where you take it and you just give it a dot that represents a valence electron. Now, if you had more, you would start circling your molecule until you put 1 on each side, and then you start doubling them up if they have more than 4. Okay, but hydrogen does not, right? Y'all told me hydrogen only has how many? 1. Okay, so I have 2 hydrogen atoms that have 1 valence electron each. And what else do I have? I have an atom of oxygen. And what does oxygen have? 6. So I'm going to do 1, 2, 3, 4. And then what do? I'm going to double them up. Doesn't matter where, 5, 6. Right? These are called Lewis dot diagrams. Right? All it does is it shows the number of valence electrons. Now, when you draw a Lewis structure, you are going to combine all of the atoms that are present in the compound in such a way that they complete their octets. So how many does oxygen need to get an octet? It needs 2 more, right? Okay, how many does hydrogen need? Only 1, because hydrogen's kind of weird and he's happy to look like helium, right? Okay, this other one needs 1. So we're not going to give and take electrons anymore. We're going to share electrons. And we share those electrons. Shared electrons are bonds. We call them. When we say this is a bond between atoms, all it is a pair of shared electrons. So shared electron pairs, so it must be two, are bonds. So if I want oxygen to have a complete octet and hydrogen to have a complete octet, what you do is you put one element in the middle and your other elements on the side. Now, how do I know that oxygen is going to be in the middle and hydrogen is going to be on the ends? Well, look, hydrogen can only make one bond, so it has to be on the outside. Oxygen can make how many? Two, right? However many electrons it needs, that's how many bonds it can make. So here's hydrogen's one, here's hydrogen's one, and I'm going to go 1, 2, 3, 4, 5, 6 electrons. So remind me, what's a bond again? A pair of shared valence electrons. So I need 2 electrons. One electron comes from one atom and the other electron comes from the other atom. So I draw a line to represent that these 2 electrons are being shared between hydrogen and oxygen. I draw another line, it's shared between hydrogen and oxygen. Does this give each atom in the molecule a complete octet? It does. So hydrogen, you count a line as 2. So on hydrogen, I'm going to count 2 and hydrogen's happy. This hydrogen has 2, hydrogen's happy. Now let's count oxygen. Count your bonds first. This one's 2, 4, 6, 8. Do we satisfy the octet? Yes, and that is a correct Lewis structure. Now, I'm going to tell you that molecules don't actually look like this technically, and I'm going to teach you this in a little bit, but I hate to teach you wrong. So actually, electrons are all the same charge, right? They're all negative. So they're all going to try and get as far away from one another as possible. So the actual structure of water looks more like this. Okay, now I'm going to teach you why in just a little bit, but I'm going to draw every molecule that I draw, I'm going to draw in the correct 3-dimensional shape so that you don't start looking at it and going, why did she do that? I'm going to draw it in the right shape, but we're going to do a few simple molecules and then I'm going to teach you about 3D shape. Okay. All right. Now, there's an easier way to do this rather than draw all your dots. It's called the needed, available, shared. Anybody heard of that before? Oh, we got 1. I think that's better than 2, better than last semester. Okay, so I call it needed, available, shared. So needed, I write it here, needed, available, and shared. All of this is talking about valence electrons. Okay, so let's do this same method with water. How many electrons total, valence electrons total in the molecule does water need to be happy? Hydrogens need how many? Right, we have H2O. Hydrogens need how many? Like total, not how many am I going to add, but how many total does a hydrogen atom need to be happy? 2. It needs 2. Now, there are how many hydrogen atoms in this molecule? 2. So 2 times 2 covers our hydrogen. Now, add to that your next atom. Your next atom is oxygen. How many valence electrons does oxygen need to be happy? It needs 8. And how many oxygen atoms do I have? 1. So total this up. What do you get? 2 times 2 is 4, plus 8 is 12. So in order to be happy, this molecule needs 12 valence electrons. But how many are actually available? How many valence electrons does hydrogen have? 1, and I have 2 atoms of hydrogen. How many valence electrons does oxygen have? 6. And how many oxygen atoms do I have? 1. So how many do I actually have? I only have 8. If I only have 8, but I need a maximum of 12, the difference between the two will tell me how many I need to share. So how many valence electrons do I need to share? 4 valence electrons. Now, how do I go from valence electrons to bonds? I divide by 2. So the number of valence electrons, so I'll put number of valence electrons divided by 2 tells me bonds, right? Okay, so how many bonds do I need to make? 2. Yeah, and bonds. How many bonds did we put in water? 2. So if you have 3 atoms and I can only make 2 bonds, I need to hook my outer atoms to my center atom. The other thing that you can tell what's going to be your center atom is the most electronegative, the most electronegative atom. How do you know on the periodic table what is the most electronegative? I will tell you, you see F up there, fluorine? I have a name for fluorine. I call her fluorine the floozy because fluorine will take electrons from anyone, right? So the closer you are to fluorine on the periodic table, the more electronegative you are. So most electronegative atom is in the center. So this is the closest to fluorine the floozy. Closest to fluorine, right? Fluorine is your most electronegative atom ever. So that's why I call her fluorine the floozy. Just, just a fun way to do it. Okay, so the last thing to check is to look at how many you had available and how many you shared. So how many were available? 8. So our available is 8. And then our shared, how many did we share? Minus 4. What do we have left? 4 electrons. Where do those 4 electrons go? They're lone pairs. So if I put my most electronegative oxygen in the middle and I put a bond to each of the flanking elements, now I still have 4 electrons that need to be assigned. Can I put them on hydrogen? No, hydrogen's full. So where do I have to put them? On oxygen. Wow. Trying to do a dot there. So I have to put them on oxygen. Okay, cool. All right, so let's do some more. Let's see. What was our next one? Our next one is B is C3H8. I like to do needed, available, shared, but there's really something sort of interesting about carbon that you should kind of remember. So carbon always wants 4 bonds or 4 interactions. And we're going to talk about carbon compounds for a very long time. So that's kind of one thing to keep in mind, but we'll still do the needed, available, and shared. So how many do I need in carbon? The question is like 2 or 8. What does carbon want? Carbon wants 8. Carbon wants a complete octet. Okay, how many carbon atoms do I have? 3. So 8 times 3 plus hydrogen. How many valence electrons does hydrogen want to be complete? Only 2. Be careful with this. Hydrogen always wants 2. How many hydrogen atoms do I have? 8. Okay. How many total do I have needed? 8 times 5, 40. Right? Okay, now the question is how many do I have available? Carbon has how many? 4. How many carbon atoms do I have? 3, plus hydrogen has how many available? Hydrogen's in group 1, so it has how many valence electrons? 1. How many hydrogen atoms do I have? 8. So how many are actually available? Only 20, right? 12 and 8 and 8, 20. So if I subtract the 2, how many do I need to share? I need to share 20 valence electrons. So if I convert that to bonds, how many bonds is that? 10 bonds. So let's see if I can make that happen. So carbon is going to be in the middle. Hydrogen is always going to be on the side because hydrogen can only make 1 bond. So I'm going to put my carbons in the middle. And now I need to attach hydrogens and attach carbons to hydrogens in order to make this work. So I'll put a hydrogen on each end. That's using up 2 hydrogens and 2 bonds. I'll connect my carbons. So now I've used 1, 2, 3, 4 bonds. Then I'm going to start giving these carbons hydrogens. So that's 3, 4, 5, 6, 7, 8. I used up 8 hydrogens. How many bonds did I do? 3, 6, 7, 8, 9, 10. Okay, do I have any left over? Available minus shared. Available is 20, shared is 20. 0. So do I have any lone pairs to assign to this molecule? No, I'm done. So you could do your dots and you could connect your dots and that kind of thing, or you can do this way. It does not matter to me which way you do it. Okay, C. What is C? N2. All right, so let's do needed, available, and shared. Nitrogen needs how many? 8. How many atoms do I have? 2. So how many do I need? 16, right? Available. Oxygen has how many? Oxygen has 6. Oh, am I doing nitrogen? Oh, I'm doing nitrogen. Oh, sorry, y'all. Okay, nitrogen has 5. How many nitrogen atoms? 2. You're all really quiet today. You don't have to be quiet. Okay, so how many total? 10. So needed minus available gives me 6 valence electrons that are going to be shared. I divide that by 2 and I get 3 bonds. Okay, so if I just have 2 nitrogen atoms and I put 1 bond, do we have a complete octet? No, we don't. We need to put in 3 bonds. How are we going to put in more bonds? You could make double bonds, triple bonds, right? So to make that, we just make a triple bond between the nitrogens, right? Okay, so now what do I do? My available minus my shared. How many did I have available? 10 minus my shared, which was 6. What do I have left? 4 valence electrons. Where am I going to put those 4 to make sure everybody has a complete octet? Does anybody have a complete octet? No. Like this nitrogen atom has 2, 4, 6. This nitrogen atom has 2, 4, 6. So they both have 6. How am I going to make sure they get their complete octets of 8? Give each atom a lone pair. So when you're drawing Lewis structures, you always draw those extra electrons as pairs. Always, always, always. If I'm going to do an electron dot diagram of nitrogen, 1, 2, 3, 4, 5, they can be by themselves. But if you're drawing the molecule, you always put them in pairs. Okay. All right. Last one, D. SiF4. Okay. Needed, available, shared. Do y'all like having a little formula to do? Does that, yeah? Okay, so needed. Si, how many? How many? What group is it in? Oh, I'm doing, haha, 8, right? You have 4 available, you need 8. How many of these atoms do you have? Only 1. Okay, fluorine, how many does fluorine need? 8. How many fluorine atoms? 4, but how many does fluorine actually have available? It has 7, and we still have 4 fluorine atoms. So how many total needed? 8 times 5 again, 40. Okay, and then 8 times 4 available, 32. So 40 minus 32, how many are we going to share? 8 divided by 2 gives us 4 bonds. Are we going to have lone pairs to assign? Let's check. Available minus shared. So what's my available? 32 minus shared, which is 8, gives me, wow, how many? 24. I'm going to have to assign 24 electrons. Let's see if we can do that. What is going to be my center atom? Say again. Silicon? Fluorine, what's fluorine? Si, my center atom can't, so it's true. Fluorine is your most electronegative atom, but it's the atom closest to fluorine. Fluorine doesn't like to be a central atom because how many electrons does it need to gain? Just 1. So it's like hydrogen. It can only make 1 bond. So when you're drawing molecules, it's the atom closest to fluorine the floozy, not fluorine the floozy. I know that's kind of confusing, isn't it? But it's not fluorine the floozy. So you have to think about how many bonds can be made. If you can only make 1, you can't be a central atom. Okay, so I'm going to make silicon my central atom. And a lot of times, I'll tell you a little trick. The first atom tends to be the central atom. Not always, but tends to be. Okay, so now what am I going to do with my fluorines, my floozies? Where am I going to put them? I have 4 of them, so I'm going to put them around silicon. There we go. Okay. So now I have 4 bonds. Can I link them together with 4 bonds? Absolutely. Now I have 24 electrons. What do I do? Silicon's got a complete octet, 2, 4, 6, 8, but do the fluorines? No, they have 2, 4, 6, 8. So that's 6 electrons around each, 6, 12, 18, 24. That will use them all up. So, yeah? Okay. How are we doing? Feeling good or feeling not so good? Can I get a, like a, we got some, okay, well, we're gonna keep doing it. We're gonna keep doing it. I just kind of want to see how we do it. All right. Okay, so we got a few more. All right, where are we, 32? Okay, so CH3Cl, CHCl3, CHCl3. Okay, so do you see how carbon's in the front? That's going to be your central atom. And it's the most electronegative that can take more than 1 electron, because chlorine is just like what? Fluorine the floozy, it can only take 1 additional electron, so it can't be a central atom. Okay, so let's do this. Needed, available, shared. Carbon needs how many? 8. How many carbon atoms? 1. Hydrogen needs how many? Be careful. 2. And I have how many hydrogen atoms? 1. Chlorine needs how many? 8. And I have how many chlorine atoms? 3. Okay. How many valence electrons are in carbon available? 4. And I have 1 atom. Hydrogen, I have how many available? 1, and I have 1 atom. Chlorine, I have how many available? 7, and I have how many atoms? 3. Okay, so how many total needed? $34. How many available? 26. Okay, so I get my difference, 34 minus 26, I get what? 8 valence electrons. I'm going to divide that by 2 and I get 4 bonds. Okay, now am I going to have some extra things to assign? Available minus shared. Available, I had 26. Shared, I had 8. So what's my difference? 18 valence electrons left to assign. Okay, so let's see if I can do this. I'm going to put carbon as my central atom. Now what? Now I'm going to put things around carbon, right? Because hydrogen and chlorine can only accept 1 more electron. So they can only participate in 1 bond. So I'm going to have to do this. And it doesn't matter which one you pick the hydrogen as. Okay. Does carbon have a complete octet? Yes. Does hydrogen have a complete octet? Yes. Do the chlorines have complete octets? No, they are so unhappy. So we need to give those chlorines those 18 electrons. How many electrons should we give each chlorine atom? 6. Come on. Yeah. Okay, let's try another one. Okay, what do we got? B is AsCl3. Okay, needed, available, shared. Needed, how many? 8. How many atoms? 1. Needed? 8. Number of atoms? 3. Okay, available. How many? 5, 1 atom. Available in chlorine. 7, 1 atom. Add them up. What do you get? Chlorine's 3. Oh, thank you. That would make a difference. Okay. How many got needed? 32. Available, somebody said 26. So what's our difference? 6 divided by 2 tells us 3 bonds. Are we going to have lone pairs left to assign? Yes. How many? Available minus shared. Available is 26 minus 6. We get 20 valence electrons to assign. Okay. So let's go and build this. What should be our central atom? Yes. Okay. Now what happens? I'm going to put 3 chlorines around it. Now, you don't know the 3-dimensional shape. That's okay. But I'm telling you, it's going to look something like this. And that's you don't have to know why yet. But I'm telling you, it looks like that. So we're going to give each one bond a chlorine. So now I've used up all my atoms. Is anybody happy? Nobody's happy. So let's give to our central atom first. How many does the central atom need? 2 lone pairs. And the reason we have this shape here is this lone pair takes up more space than this bonded pair. The bonded pair, the electrons are hanging out with each of the atoms, and so they don't take up as much space, where these are only hanging out with one atom. And so they end up taking up more space. So that's why you get these weird 3-dimensional shapes. So how about chlorine? How many should we give chlorine? 6 each. So does that 6, 12, 18, and then the last 2 are central atom. Do we have a complete molecule? Yeah. Isn't it nice? I think it's kind of nice to have a formula that you can always go back to and use. Okay, Cl2. Now, Cl2, you could just look at Cl2. How many bonds can Cl make? Only 1, right? If I drew a Lewis dot diagram of chlorine, 1, 2, 3, 4, how many valence electrons? 5, 6, 7, right? And then I drew another chlorine, 1, 2, 3, 4, 5, 6, 7. Then what do? Share these 2 to make a bond. You don't have to use the needed available shared for everything. Some of them you don't need to, but if you did need it available shared, would it work? Absolutely, it will work every time for the problems that I'll give you. There are some exceptions, but I'll never give you one that's an exception to the needed available shared. Okay, C2H2. Y'all want to do needed available shared, or you want to do it freehand? And do both? Yeah, okay, let's do both. Let's do both. Let's do the freehand first. What's going to be in the middle of my molecule? Carbons or hydrogens? Carbons. So I'm going to put my 2 carbons. I know each carbon has to have a bond to the other carbon. And then I'm going to attach what else to each carbon? Hydrogen. Let's kind of be fair, right? Spread it out a little bit. Okay, now, carbon had how many valence electrons? 1, 2, 3, 4, 1, 2, 3, 4, right? Okay, is anybody happy in this molecule? What? Yeah, who's happy? Hydrogen's happy. Are my carbons happy? No, they're not. So how can I make carbon happy? I don't have any more electrons to put. So what should I do instead? I need to make some more bonds, right? So I'm going to share these 2 electrons here and here. So really, what should my molecule look like? I drew that as dots, and that looks kind of terrible, right? So really, you should have a hydrogen, a carbon, and how many bonds between the carbon? 3. But that's just what it means, right? Sometimes it's nice to be able to connect the dots. Okay, you want to do needed available shared? Okay, carbon, how many does it need? How many? 8 times 2. Hydrogen, how many does it need? 2 times 2 atoms. I get how many? 20. Available in carbon. 4, I have 2 atoms plus hydrogen has how many? 1, and I have how many atoms? 2. So how many available? 10. So shared is 10 divided by 2. 5 bonds. Now, do I have any lone pairs to assign? Available minus shared, 10 minus 10, 0. So there are going to be no lone pairs. So I have 5 bonds, and I need to hook everything together, right? So I initially just put bonds to the hydrogens, and I can't put any more bonds to the hydrogens. So then I must put the bonds between the carbons to complete the octet. Either way, you get the same answer. Okay. All right. Okay. So moving on. All right. So now, how do you know just by looking at something that it's a covalent compound versus an ionic compound? Right, so let's see if I can move this. I wrote it up here. If you have a non-metal and a non-metal, you're making a covalent compound because all they're going to do is share electrons. How do you get an ionic compound? You have a metal and a polyatomic. That's a possibility, right? You could have a metal and a non-metal, or you could have a polyatomic and a non-metal. And in some rare cases, you can have a polyatomic and a polyatomic to get an ionic compound. Okay, but this is how you figure it out. So just look and see, is it a non-metal and a non-metal? It's covalent, otherwise it's ionic. Okay, so K2O, what is K? Metal, because it's on the left. O is non-metal, so it must be ionic. I'm just going to put I or C. CO2, we have two what? Two non-metals, so must be covalent. Excuse me, GAF. GA, what is it? It's a metal, it's a metal. How about F? Non-metal, so a metal and a non-metal, ionic. C2H6, what do I have? Two non-metals, carbon and hydrogen. Now hydrogen's on the left, right? But is hydrogen a non-metal? A metal, excuse me. No, it's a gas, right? Metals aren't gases at room temperature. They're not. So really, hydrogen should be over there, but it doesn't have 7 valence electrons, so we leave it on the left. So hydrogen is kind of weird in that it can kind of be in two places on the periodic table. So this is a non-metal and a non-metal, so it must be covalent, right? Okay, NiCl2, nickel is a metal, Cl is a non-metal, so a metal and a non-metal, ionic. BaSO4, Ba is barium, it's a metal. SO4, that's a polyatomic ion. That is a polyatomic ion. So a metal and a polyatomic, that is a ionic compound. SO2, go this way. Sulfur is a non-metal, oxygen is a non-metal, so it is covalent, non-metal and non-metal covalent. NO2, nitrogen and oxygen, both are non-metal, so they are covalent. NH4Cl, do we just look at the N? No, NH4 is one of those polyatomic ions. Look at the third one on your polyatomic ion chart. So that's a polyatomic and a non-metal. So what is it? Ionic. SiH4, silicon. Now this is a little bit tricky. What is Si? What kind of an element? It's actually a metalloid. So in this case, we have a metalloid and we have a non-metal, and that makes it covalent. So this is kind of weird because you have a metalloid and a non-metal. Not really a metal, so it's covalent. Okay, cool. All right. Oh yeah, and I made an error on the video. Did anybody catch it? I said, yeah, I said H2O. Sometimes, you know, elements swirl around in my brain. So H2O is not dinitrogen monoxide. What is it? Dihydrogen monoxide. Now you know they did this thing at some other universities where the students did this thing to petition you shouldn't ingest all these harsh chemicals and all this kind of stuff, and it was a ban on dihydrogen monoxide. But people believed it because they don't understand chemistry. Is dihydrogen monoxide bad? No, it's water. You need it to survive, right? So if you understand chemistry, you're just going to have a better ability to make actually informed decisions, I believe. All right. So when we're naming our compounds, our covalent compounds, we're not going to do the same sort of deal that we did with ionic. It's a little bit different because when you're doing covalent compounds, if you have more than one atom, you use a prefix. What are our prefixes? Do I give you? I think I give you the prefixes. Do I not? Do I give them to you? I thought I did somewhere. Yeah, I did. I did right here. So I tell you the number and I tell you the prefix. So it's on your best friend. So turns that on your best friend, right? You have the table. So if you have one atom, it's mono. If you have two, it's di. Three, it's tri. So okay. So y'all know where I'm getting this information from. All right. So you have to make sure that it's a covalent compound. Now they say it in this question, but it's always good to like make sure, am I naming an ionic compound or am I naming a covalent compound? Nitrogen and oxygen are both nonmetals. So we're going to name it as an ionic. So what does the 2 mean? Di. So this is dinitrogen. And 4 tetraoxide, but we don't put 2 vowels together. So you drop one of the vowels. So it's just tetroxide. But if you put the A, I don't care. I'm not that picky. Okay. Carbon monoxide. Why doesn't this carbon have a prefix? Because if it's the first atom and you have one atom of that element, you don't put the mono. Okay, so what should my formula look like? Carbon monoxide. 1 carbon, 1 oxygen. So just CO. Okay, our next one, P2. What is the 2? Di. What is the P? Phosphorus. And then 5 is penta. P. But we don't put the A, pent oxide. Okay, carbon dioxide. We still have how many carbons? 1. Dioxide means we have oxygen, but how many? 2. Okay, NH3, what do we have? Do we say mono nitrogen? No, we just say nitrogen, what? 3 is tri, and then hydride, right? You're going to do the same thing, the IDE, just like you did for an ionic compound. But in this case, you're using prefixes. Anybody know the other more common name for NH3? Ammonia. There's ammonium and ammonia, and this is ammonia. Okay, so yeah, we didn't get season. That's okay. Okay, it's okay. So I'll revamp. What are we time? No, we still got 20 minutes. We still got 20 minutes. What am I thinking? We still got 20 minutes. Yay, we're doing great. Okay. All right. So the next thing that we have to talk about is how can we count atoms? How big are atoms? However small you think atoms are, they're smaller. They're really, really, really small. So if you have a gram of something, you actually have a ton of atoms of whatever substance that is. And it's kind of hard to count that. You end up with lots of zeros. And in science, what do we do when we have lots of zeros? We tend to put it into scientific notation. So a lot of times when you're saying number of atoms of something, it's, 5 times 10 to the 23rd, right? It's a lot. And so scientists have come up with a way to count atoms that makes it a little bit easier. So just like we count eggs, how do we count eggs? By the dozen, right? They're relatively big. How do we count sheets of paper? By the ream, right? A ream of paper is like 500 sheets of paper, right? Like a pack of paper, same thing, right? So there are multiple instances of us using that in our lives. And so basically what scientists have said is 6.02 times 10 to the 23rd is a mole. And that's a counting number of anything. You could have a mole of M&Ms. That would be a lot of M&Ms. that would be a lot of M&Ms, because M&Ms are relatively big, right? But atoms are so tiny that in order to have a significant amount of them, you're going to have a crap ton of them, right? So it's just another way to count. So look at 3.38. Compare the number of atoms and the number of grams present in 1 mole of helium and 1 mole of argon. So let's do helium first. So what are we going to do if we know we have 1 mole? Let's put all of our things that we know. 100 moles of what? Helium, He. So whenever you're doing math like this, remember to put your units and remember to put what element it is, what substance it is, right? All that information. So what was the relationship between a mole and atoms? Because that's what we're looking for in A. No matter what substance it is, if I have 1 mole, how many atoms do I have? Times 10 to the 23rd atoms, right? So how many do I have? All you do is multiplying by 1, dividing by 1. So 6.02 times 10 to the 23rd atoms. That was the definition of a mole, right? So if I have 1 mole of argon, how many atoms is that? Same thing, 6.02 times 10 to the 23rd, because by definition, there are 6.02 times 10 to the 23rd atoms in 1 mole of anything, argon included. So that's helium, atoms, and this is argon, right? That's the definition. Now, the question is, how is that different in terms of grams? Before we do the math, if you look at the periodic table, look at the mass of helium. What's the mass, the atomic mass of helium? 4. What's the atomic mass of argon? Go 2 elements down. 39.95, so about 40. So it's about 10 times heavier. So what do you think the number of grams are going to be? About 10 times heavier, right? So let's see if we can do the math on that. Okay, so I'm looking for my eraser. I'm going to try and put it all in here together. Okay, so I know, right, my relationship between atoms and moles, but there's another relationship with moles, and that is moles to grams. So I know for any given element, right, 1 mole is equal to the amount of grams that is the atomic mass of the element. So for example, helium, 1 mole of helium is equal to 4.00 grams of helium. What about argon? 1 mole, this is supposed to be helium, of argon is equal to how much? 0.95 grams of argon, right? So I can use these as dimensional analysis conversion factors. So if I start out with 1 mole of helium, I use this as a conversion factor. In 1 mole of helium, I have how many grams? 4 grams of helium. So in 1 mole, how many grams? 4 grams, right? How about argon? And 1 mole of argon, I know for every 1 mole of argon, I have how many? 39.95 grams of argon. My moles cancel, I'm left with grams. I get 39.95 grams of argon. Does that make sense? Absolutely. Absolutely. Right? It has more protons, it has more neutrons, therefore it's heavier. So a mole of it is going to weigh more. Compare like a regular M&M and a peanut M&M, right? Which one weighs more? The peanut M&M weighs more. So if you had a mole of regular M&Ms and a mole of peanut M&Ms, which one would weigh more? The mole of peanut M&Ms, right? It's the same thing, same thing. Can you tell I like M&Ms? Prefer the peanut ones too. Okay, calculate the following. The number of sulfur atoms in 0.660 moles of sulfur. Let's do this. So we're going to start out with 0.660 moles of sulfur. I'm trying to get to atoms. Do I have a conversion factor where I can put moles on the bottom and atoms on top? Yes, I know in 1 mole of sulfur, there are how many atoms? O2 times 10 to the 23rd atoms of sulfur. So put it into your calculator. You need to hear some click clacking. Oh, my second favorite sound in the world. Opening calculators. Okay, so what do you get? Ten to the 23rd atoms sulfur. Good. Okay, B, the number of moles in 15 grams of iron. So I have 15 grams of iron. Oh, is that the right number of sig figs? Yes, it is. Yes, it is. 3.97, we have 3, and 0.660, we have 3. Okay, so 15 grams of iron. So I know I have to put grams at the bottom. Do I have a conversion factor that takes me from grams to moles? Yeah, I do. I know in 1 mole of Fe, I have how many grams? Not 19. Look on the periodic table, look at the red number under the 55.85 grams. So what do I get? 0. I got 269. Is that what y'all got? So look at this. You have 15 grams of iron and you have almost 0.3 moles, not even a mole. And you've got 15 grams of iron there, right? A mole is huge. A mole is huge. Okay. The number of moles in, oh no, I did that. C, the number of atoms in 66.0 grams of copper. Okay, so I want to get rid of grams and I want to go to atoms. Do I have that conversion? No, so I'm going to have to go in multiple steps. What do I know that I can get rid of grams? Moles. So I know in 1 mole of copper, so if I look at copper, the number at the bottom, I have how many grams? 63.55, right? So now I've gotten rid of grams. but I'm still in moles and I want to be in atoms. So I got to put moles on the bottom. And I want to go to atoms on top. So in 1 mole of copper, I have how many atoms? 6.02 times 10 to the 23rd atoms of copper. So what do I get? Did I want atoms? Yeah. What do you get? How much? 5 point what? 6.25. And this is atoms of copper, right? Okay. Now, when we look at substances, right? Substances aren't just made out of one element. They're made out of multiple elements, right? What's that? They're made out of multiple elements. So multiple elements put together make up a molecule. So the mass of the molecule is then dependent upon the mass of each of the individual atoms. So that's what we call a molar mass. What is the mass of the entire molecule? So 3.42, determine the molar mass for the following compounds. Ethylene. So you know when your bananas turn, right? There's a gas that's being produced that speeds that up. So if you take like a really ripe banana and put it with your fresh bananas will ripen faster because the old one is producing ethylene gas. It's true. Okay. You could actually put, like, if you get mangoes at the store, this is kind of interesting, and they're not ripe yet, and you want to speed up the ripening process. If you put them into a bucket of rice, the rice will actually kind of seal it and keep the ethylene gas inside around the mango, and it'll ripen it. Works with like any fruit. Kind of cool, right? Things you never knew you wanted to know. Okay, so we want to know the molar mass. How do we figure out the molar mass? We need to figure out each of the individual components. So what is carbon? What? Carbon has a mass of 12.01. So we'll do C2H4. 12.01. But how many atoms of carbon do we have? That's in grams. So we have 2. So we're going to multiply that. Now we need to add to that our hydrogen. What's the molar mass of hydrogen? 1.01. And how many do we have? 4. Okay. So everything that you see, and like I don't have room for units, but I'll put units at the bottom. It's really grams per mole, right? Because that's what we just talked about. Well, here's the mouse. I'm trying to find the wrong thing. So multiply 12.01 times 2, add that to 1.01 times 4. What do you get? What do you get? Calculators. .0. Now, how many sig figs am I going to go? So I usually go, if you look on the periodic table, all of the elements go to at least 2 places past the decimal. Some of them will go 3, depending on the periodic table that you use. This one's going 2. What does yours go to on your best friend? Your best friend goes 2, except for hydrogen and helium. So at least go to 2 on everything. So this is grams per mole. Okay, so that is the mass of 1 mole of this compound, right? It depended upon all the individual elements in that compound. Let's do the same thing, citric acid. This is why fruits taste so nice and sour. C6H8O7. So carbon has a molar mass of what? 12.01. How many do I have? 6. Hydrogen is 1.0. Yours does 008. Doesn't matter. This one in the classroom does 1.01. doesn't matter. Times we have 8 atoms. Oxygen, what's the molar mass of oxygen? 16.00 times how many do we have? 7. Put that in your calculator. What do you get? I got 192.12. Is that what y'all got? Okay. All right, let's do C up here. Sodium bicarbonate. Sodium, this is what we're doing. Sodium has how many? Has what mass? 22.99, and there's only one of them. Hydrogen has how many? Has what mass? Oh my goodness. 1.01. Carbon, mass of 12.01. And oxygen is 16 times 3. What do you get? I got 84.01. Is that what y'all get? Yeah. Okay. So I guess we will stop there. That's pretty good. That's pretty good. We'll have one review and then we'll talk about models. We don't have much left, so it'll be okay. All right, y'all have a great rest of your day. Let me mark where we were. 4.2. We're going to go start with 3.44 tomorrow. All right. Anybody on Zoom have any questions? Anybody on Zoom? Any questions? Otherwise, you're free to go. Okay, I'm going to go ahead and end the chat if nobody has it.